and some of the new IOL technologies that are actually coming for cataract surgery. So let us start. Let us first focus on what do we understand by defocus curve and how it is generated. Now, most of this is already explained in my blog quickguide.org, and there in an article understanding defocus curve of multifocal IOLs, I had said that the starting point of any defocus curve is to make the patient best corrected to 6 by 6 or 20/20. So if you are doing a monocular defocus curve, you should start here by making the patient best corrected, letting the patient see 6 by 6. If the patient is already monocularly seeing 6 by 6, then you don't need to further best correct the patient. Now, with the defocus curve, what are we trying to see? In the defocus curve, what we are trying to understand the lens function, what the lens is capable of giving to your patients, and not what the patient is seeing after the implantation with the IOL. Now, these are two different things. What the patient says after implantation with the intraocular lens may be a function of IOL calculation, biometry, your capsular exercise, therefore ELP. We are not trying to see what the patient is saying. So therefore, you best correct the patient to 6 by 6 so that you only you know test the lens performance, keeping all other confounding factors aside, right? So your start point is best corrected 6 by 6, and then you dial this minus lenses, the negative lenses over here. And what these lenses mean is that you are dialing lenses, which means Vergence distance from the eye, right? So for example, if you have dialed a minus 1.5 diopter lens, this would mean that you are making the patient read this Snell's chart at a distance of 65 centimeters from the eye, which is a kind of intermediate vision, which is related to your laptop work, the everyday that you type on your laptop. That's probably around 65 to 70 centimeter of your eye. So if you're dialing minus 2.5, that would mean a 50 centimeter, a 40 centimeter Vergence distance of 40 centimeter from the patient's eye to the Snell's chart, right? So by dialing these lenses, you are recording the patient's vision, and you understand actually what the patient's near vision could be. For your vast majority of patients, the near vision, the intermediate vision will be, right? So what happens is that when you have not defocused the patient, you have made the patient best corrected. That's the starting point, 0, 0. Your distance focal point is on the retina, and if this is a bifocal, I'll say it has only one extra focal point, which is near focal point. It is before the retina. But as you dial this minus lenses, the distance focal point goes defocus. I mean, it goes behind the retina, and the near focal point slowly comes forward and sits on the retina as you dial those minus 2, minus 2.5 diopter lenses. That depends upon the add power that is actually built in the lens. For example, if the lens has an add power of 3 diopters, then probably it would be minus 2. It would be an add power of 2.5 diopters on the spectacle plane. So when you dial minus 2.5, you will see that the patient's vision again peaks because the near focal point sits on the retina. So full explanation of the defocus curve, as well as it has some limitations like pupil size, you need to have a standardized pupil size. So all these things are actually there in my article in quickguide.org. Now, moving ahead, how do we classify the different IOLs that are available in the market? So the ESCRS task force recommendation in 2024 was that, test the patient at point to log mark. What is the patient seeing at point to log mark? If the IOL is giving your patient more than 2.3 diopters of full range of vision, then that must be a full range of vision IOL, that is trifocal IOLs, right? The presbyopia correcting IOLs. If the patient at 0.2 logmer, 0.2 logmer means 20 by 32 or 6 by 9. If the patient is getting less than 2.3 diopters, then it should be classified as a partial range of field in the IOL, right? Now, in that less than 2.3 diopters, again, you can classify it according to less than 1.2 diopters, between 1.2 to 1.58 diopters, and more than 1.58 diopters. So if the lens is giving you more than 1.58 diopters of depth of focus for your patients within 1.58 and 2.3 diopters, then it's an EDOF lens. If the lens is giving a depth of focus of 1.2 to 1.58 diopters, then it's an enhanced monofocal IOL. And that's to be recorded, and that is at zero point 0.2 logmar or 20 by 32 or 6 by 9 of the patient's vision, right? Right. So now let's focus on lenses that gives a full range of vision. That in this more than 2.3 diopters. So in this, actually, we have the trifocal IOLs and the recently launched Rayner spiral optic lens. So in the article Science Behind Diffractive Multifocal IOLs, I have explained how light behaves and what happens to light when it goes through a small opening. So it diffracts, right? And in many of my videos in this channel, you will see this explanation more, that light actually, when it goes through these two slates, it basically spreads out into two wave fronts. And when it spreads out and and becomes two wave fronts, then there will be an interference of light. And because of this interference, that is constructive and destructive interference of light, you will see, if you put a screen here, you will see this light and dark phenomenon, light and dark phenomenon. Wherever there is this constructive interference of light, that is the high of one wave is meeting the high of another wave, then you find this light phenomenon. And basically, we call this as orders, because the zero order for most lenses is the distance focal point, and the plus one order is the intermediate focal point, and the plus two order is the near focal point. Wherever there is a destructive interference, there is a light loss, and you will have this dark regions over here. Light loss is also because light also goes to the third, fourth, and fifth orders. So light, when it strikes this steps, actually it spreads, and when it spreads, it goes to the zero order, plus one order, plus two order. For most lenses, zero order is the distance, that is the refractive base curvature, that is the monofocal lens on which the steps are built. The monofocal base curvature is also refracting to the zero order, right? The rays of light to the distance zero order. So the steps are built in such a way that the zero order is also the distance focal point, plus one is the intermediate focal point, and plus two is the near focal point. Now, the distance between the steps actually means how far is your near focal point from the distance focal point. That is what is the add power of the lens, right? And here I have explained in terms of the bifocal IOLs that higher the add power of a lens, the diameter of the first bullseye, the first step, the diameter of the first step is lower. But if you come down with your add power, then the diameter becomes bigger. So these explanations are there. You could actually, search in my blog, Science Behind Diffractive Multifocal IOLs, and then you will get the article. Now let's move on to another topic here, and is the defocus curve, right? So we did talk about how a defocus curve is generated. Now, for most multifocal, trifocal IOLs, you will find that you have a peak distance and peak intermediate as well as near vision, but between the distance and the intermediate, the vision kind of drops. Right here, you can see this defocus curve with PanOptix and Synergy. Both the lenses have a dip at the far intermediate, around 80 to 100 centimeters, right, or 122 centimeters. You have actually a drop. Now, companies are trying to today to bring this trifocal IOLs on the EDOF platform. One example could be that you had the EDOF lens Symphony, and then they launched the Synergy lens on the Symphony platform. So what they're trying to do is that not only give the patient an intermediate and near vision with the trifocal IOLs, but also provide fill up the vision in these areas also by launching their trifocal IOLs on the EDOF platform, right? So that the vision does not fall, uh, you know, even at the far intermediate. Now, coming to the Rayner spiral optic design lens, this lens is a 6 millimeter optic lens, but it is divided into these zones over here. The first zone, 1.3 millimeters, 0 to 1.3 millimeters, is dedicated for the distance. Then from 1.1 to 3.3 millimeters, I believe, is for the spiral optics, right? And beyond that, 3.3 to 6 millimeters is the zone for the distance focal point again. So if you look now into zoom into this spiral optics design over here in the middle, they have they probably would have these two spirals fanning out, right? So it kind of, the two spirals have two alternate powers, the near and the intermediate power, and this could actually fan out like this in the spiral optics region. So that basically is the spiral optics design. You can go into my website, Rayner Spiral Optics Design IUL, where I give a full explanation of this lens. So if you go into the website of the Rayner lens, you will find that they have provided a defocus curve, and in that defocus curve of less patients, though, like 25 patients, you kind of see that the best corrected vision, and then the it kind of maintains the patient's vision at far intermediate to intermediate, right, around 6 by 6. So that's how they kind of fill it up here. Now let's also look into the enhanced monofocal or the EDOF lenses. And as I said before, lenses that provide depth of focus of less than 2.3 diopters at zero point 0.2 logMAR or 20 by 32 or 6 by 9 are actually called either an EDOF lens or an enhanced monofocal lens or a monofocal lens. Now, the American Academy of Ophthalmology task force defines an EDOF lens as a lens that provides zero point 0.5 diopters greater depth of focus than the monofocal IOLs, right? So that is basically the definition from the American Academy of Ophthalmology. Now, before we understand these lenses, how they work, it is important to understand what is a positive and what is a negative spherical aberration. So, the positive spherical aberration is one where the marginal rays of light are falling before the paraxial rays of light, and the negative spherical aberration is one where the marginal rays of light are falling beyond the paraxial rays of light. So this is the paraxial rays of light or the central rays of light over here falling here, and the marginal rays of light are falling beyond the paraxial rays of light. So this distance over here is called the spherical aberration, right? It's basically the longitudinal spherical aberration. That's negative because the marginal rays of light are falling beyond the behind the paraxial rays of light. Similarly, here, this region is the positive spherical aberration region between the paraxial focus and the marginal focus. And you have, this region as the positive spherical aberration. Here, the best focus, I mean, where will the patient's best focus be? And in terms of positive or negative spherical aberration, it is neither on the paraxial focus nor on the marginal focus, because things will be blurred because not every light is coming to one point. So, so the best focus of the patient or the best image will be somewhere closer to the marginal focus. It's around one third away from the marginal focus and two thirds away from the paraxial focus. So that is basically the how in my article actually I have described how you can find out the best focus in case when there is a positive and negative spherical aberration. All right, so let's move ahead and uh, one second, I'm just struggling with this. All right. So now a question comes whether a positive spherical aberration is beneficial for a higher depth of focus and image quality rather, or a negative spherical aberration lens is better. And I would say it depends. I mean, for an emmetropic patient, there are studies and counter studies though, and I have written about this in depth about Caroline Rocha actually and co-authors found that higher positive spherical aberration provided better distance corrected near visual acuity, better depth of focus than negative spherical aberration. And on the contrary, there was other papers by Kozai and co-authors who found that no, negative spherical aberration provides probably a better depth of focus. So there are counter studies and studies. My thought is that, going across many studies, both positive and negative spherical aberration lens can actually provide you a good depth of focus. The question is that, does the patient land emmetropia? If the patient lands, myopia or hyperopia, then a way a lens based on positive spherical aberration works, and a way the lens based on negative spherical aberration will work is maybe different. So here you have an example of a negative spherical aberration. So this is your retina. You had an hyperopic outcome. So your paraxial rays of light are beyond the retina. And now your best focus is further away from that. Remember, one third away from the marginal focus, two thirds away from the paraxial focus. So your best focus is somewhere here, right? So if you have an hyperopic outcome, your patient's best focus in mesopic conditions will be further away, right? Because the pupil is dilating, the best focus shifts away. You already have an hyperopic outcome. The best focus further shifts away from the retina. But on the other hand, if you have a myopic outcome, that may be beneficial for a patient which has, for an IOL which has negative spherical aberration, right? For the same reason. And again, the contrary is true for positive spherical aberration. Here you have the marginal rays of light falling before the paraxial rays of light, right? And if you have a very high myopic outcome, then the best focus further shifts with dilation, pupil dilation. The best focus further shifts away from the retina. In these cases, probably an hyperopic outcome may be a little better than having a myopic outcome of the same amount, right? So that is my thought here. Now, these explanations I have given. Now, there was a paper sometime back by Smith and Borenstein wherein they trying to understand what amount of spherical aberration is added in these lenses. It may not be added actually, even sometimes when you change the optics of the lens, the spherical aberration actually can be seen with these lenses when you're changing the radius of curvature of the lens. For that, actually, they may not be deliberately added spherical aberration, but because of the change in optics, the spherical aberration becomes a byproduct. So other than the Rayner RayOne EMV, they measured that plus 0.14 microns of positive spherical aberration with the Rayner at around roughly 6 millimeter of optics, 5.8 millimeter. So other than the Rayner RayOne EMV, most of these lenses are negative spherical aberration. They are producing negative spherical aberration. For example, when Tecnis Eyhance, we know in the central 1 millimeter, they have a higher power. So with that, there leads to a higher negative spherical aberration. And I have listed out in that article which patients may find beneficial, which patients may not find beneficial with each of these lenses over here. Now, in my article, Guide to Extended Depth of Focus Optics, I have listed the four ways of providing a better depth of focus to the patients. And these are the four ways. Lenses that have a change in asphericity from the center to the periphery, RayOne EMV, that adds positive spherical aberration deliberately by changing the curvature of the lens. So there is a change in asphericity on the lens surface. Then the second group is like the Eyhance, which has higher curvature, radius of curvature in the central 1 millimeter, right? So that's the Eyhance lens. Now, the third is lenses that actually work on higher order optics. Now, the kind of what I mean by higher order optics, I have explained in this article. And the example of this is ISOPure and Impress. And the fourth is lenses that rely on changing incoming wavefront as it passes through the IOL optics. That's the VVT, right? So these are basically the four ways that currently I have found that the intraocular lenses, the Enhance and EDOF lenses actually provide a greater depth of focus to the patients. Right. So coming to the first two, what is the difference between RayOne EMV and the Tecnis Eyhance? So if you see this, Tecnis Eyhance provides in the central 1 millimeter a higher power, right? It's almost like a bifocal lens over here. So remember the bifocal glasses, the spectacles, you have higher radius of curvature over here for the patients to read. The same way in the central 1 millimeter, Eyhance has a higher power in the central 1 millimeter. And in contrast, the Rayner EMV, it is not just limited in the Rayner in the 1 millimeter of the lens, and it basically progresses in the changes the aspherity of the lens when you go from the center to the periphery, right? So adding a positive spherical aberration. Now, what I have explained in this slide is that why do you find higher negative spherical aberration with Eyhance and PureSee? Because they don't add negative spherical aberration. Yes, the Tecnis platform is a negative spherical aberration lens. They have around minus 0.275 microns of spherical aberration. But with the Eyhance, you see that there is even larger negative spherical aberration, minus zero point 0.5. And here I've explained why. Because you know what, this is say a Tecnis Eyhance lens, it's Tecnis lens, Tecnis platform lens, not the Eyhance. So you have a negative spherical aberration. Say the rays of light traveling from the periphery will fall behind the paraxial rays of light. That's negative spherical aberration, right? Now you have a raised, you have more power in the central 1 millimeter. What happens to the paraxial rays of light? They will further converge here, right? So the distance between the marginal rays of light and the paraxial rays of light increases, and therefore you have more negative spherical aberration. Same with PureSee IOL, and that is why you see here more negative spherical aberrations with these lenses, right? So this is again I have described in my blog how the PureSee works, and this is taken from the latest peer review study that came out in the JCRS, and they found out that if you order for a 20 diopter IOL, say the Biometry has called for a 20 diopter, you've ordered for a 20 diopter IOL, it absolutely in the center it starts with 19 diopter, 19.5 diopter, and within zero point 0.5 millimeter of the radius, it starts increasing. And it goes to the peak around 1 millimeter, right? Around, so it is 1 millimeter in the radius. So at 2 millimeters, it will go to a peak power of 23.5 diopters and then come down. So remember, this is on the IOL plane. So on the corneal plane, the effective power will be much less. And some studies say that the effective power could be around 1.75 diopters of depth of focus for the patients at 0.2 logmar. All right, so that's how. Now the question is, how much of spherical aberration is tolerable for the patients, right? And Juen, Tumber, and Moore actually did a study wherein they kind of tried to answer this question, and they found out that the human eye can tolerate a spherical aberration of around 0.07 micron to minus 0.15 micron, around 0.15 micron. That's the most that the human eye can tolerate. If lenses at more spherical aberration beyond this, then probably the distance visual acuity will be compromised for near visual acuity, right? So you gain depth of focus, true, but you start having a drop in visual acuity for the far focus. So that's what Juen Tabaer basically explains here. And how does the impress on the isopia work? In my view, the impress has inflection points. So basically, it is not a standard curvature of the lens. It is in free-form optics. We call it free-form optics. Again, this is explained in one of my articles what I mean by free-form optics. So they have this concavity up and concavity down. So here you have a concavity down, you have concavity up, and this is how the lens actually provides you a depth of focus, because any ray of light, each ray of light that passes through this inflection points is actually sent to a particular point, right? So it creates a series of focal points. So this basically is based on inflection points. And this is how a latest article at the JCRS actually shows the power profile of the impress lens here. The black line is the raw power profile of the IOL, and the blue is taking together the cornea. So let's focus on the black. Actually, you can see all of these lenses. provide starts with a very high power and then come down, right? So if your patient has actually a small pupil, then they will have a myopic outcome, right? You will see if the patient has less than 2 millimeters of pupil, which is very rare, but you will see that in the on autorefractometer you are getting a myopic refraction, or even in the Snell's charts, right? So the pupil diameter actually plays a role. And some surgeons do say that even with an enhanced monofocal lens, the patient is actually getting a good near. And here, authors have actually showed in which kind of patients will you find a greater pseudo accommodation. That is, the patient is reading even with the enhanced monofocal IOLs. They are just supposed to give you an functional intermediate vision, but still some patients can get good near if you have a very short axial length, or if you have axial hyperopia, or very high powered IOL, right? So then you basically have a higher amount of pseudo accommodation. Of course, we know that pupil size, smaller pupil size gives a better depth of focus also. Now, the AO task force statement on defocus curve with EDOF IOL. So, if you are doing a defocus curve to understand these lenses, so what is the AO task force asking you to do? So, do a monocular defocus curve, because binocular often actually confusing because of the binocular summation and all. So, monocular defocus curve, do a testing from plus 1.5 diopter to 2.5 diopters with zero point 0.5 diopter of increments. Now, depth of focus. Well, how do we define depth of focus? Depth of focus is defined as from zero. That is, you have now started defocusing. Remember, I started by saying best corrected vision 0, make the patient 6 by 6, not dilating any power. So that's your starting point. From there, what is the highest negative power that the patient is tolerating at a 0.2 log mod, that is at 6 by 9 or 20 by 32, right? So that's the highest negative power that the patient is tolerating at 0.2 log mod. Beyond that, it's not your depth of focus, the patient's depth of focus, right? Pupil size should be measured in the same lighting